All right, welcome to This Explainer. Today, we're diving into the pretty fascinating world of random sampling. If you've ever wondered how statisticians extract accurate data from giant populations without, completely losing their minds, you are in the right place. We're drawing straight from Unit 4, Lesson 1 of our source text to unpack exactly how we can decode the world using some incredibly clever, mathematically sound shortcuts. Let's get right into it. Here's a quick roadmap for today. We'll be covering the power of sampling, simple random samples, the calculator method, stratified random samples, and finally, proportional math in action. Kicking things off with Section 1, the power of sampling. So before we look at how we sample, we really have to establish the massive, real-world logistical nightmare that sampling actually solves. I mean, think about it. How do you pull millions of fans to award the Ballon d'Or to the world's best football player? Asking literally every single football fan on Earth to vote is, well, it's impossible. It would take years and cost billions of dollars. And that massive hurdle right there is exactly why we need a representative sample. Instead of asking absolutely everyone, we choose a small, carefully selected group, sports journalists, analysts, and experts from all over the world to represent the opinions of the entire global fan base. Now, if we look at the mass population method, which is basically gathering data from every single individual, sure, it's highly accurate, but it requires a ridiculous amount of time, effort, and money. On the flip side, the sample method saves all that time and cost because you're only looking at a fraction of the group. But, and this is a massive but, there's a huge caveat here. It risks giving you totally inaccurate results if the sample doesn't actually represent the whole population. If it's done poorly, you end up with what we call a biased sample. And honestly, that renders your data practically useless. Moving right along to Section 2, simple random samples. Let's check out our first real technique to avoid that statistical bias. This is a method that's absolutely perfect for smaller, uniform groups. A simple random sample is a selection method designed specifically for homogeneous populations, which is really just a fancy way of saying groups where everyone shares similar overarching characteristics. The key here is that it ensures every single individual has the exact same chance of being chosen. So if you're dealing with a small group, let's say picking 5 students out of a single class of 40, it's super easy. You just make identical name cards, fold them up so they look exactly the same, toss them into a box, mix them well, and draw them randomly. Boom, done. But before you start drawing names, keep this golden rule of thumb in mind. The most appropriate sample size is, on average, 10% of your total population. That's your statistical sweet spot. It gives you enough data to actually be representative without overwhelming your resources and defeating the whole purpose of sampling in the first place. So for a school of 500 students, your target sample is going to be exactly 50. Which brings us to Section 3, the calculator method. Okay, so what happens when your population is just way too big for a physical box of folded names? You really can't be folding 500 pieces of paper without your hands cramping up, right? This is where our first tech tool comes in. You can actually use a scientific calculator to pick a random 10% sample of, say, 300 factory workers. This is great because it totally removes human bias and all that manual labor by relying on the calculator's built-in random number generator. By assigning every worker a number from 1 to 300, we can magically generate our required 30 participants. Here's how you do it. First, number your population sequentially. Then, grab your scientific calculator, hit the Shift button, press the Rand key, and hit the equals sign. You're going to just repeatedly press that equals key, and it's going to generate these 3-digit decimal fractions. The calculator basically spits out random numbers between 000 and 0999. Now, to turn these random decimals into actual usable worker numbers, you just pretend the decimal point isn't even there. If it shows just one decimal place, like 0.3, you mentally add 2 zeros to make it 0.300, and just like that, worker number 300 is selected for your survey. The absolutely crucial point here is knowing exactly what to do with the wild numbers the calculator might throw at you. If 0.162 pops up, you ignore the decimal, and worker 162 is officially drafted into your sample. Perfect. But what if 0.511 appears? Well, you have to exclude it. Why? Because 511 is way greater than our total factory population of 300. You obviously can't survey a worker who doesn't exist. You also have to toss out any numbers that the calculator repeats. So you literally just keep hitting that equals key, evaluating each decimal until you have exactly 30 unique, valid worker numbers. All right, let's pivot to Section 4, layer random samples. So what if we hit a plot twist and our population isn't perfectly uniform?
Suddenly, that simple random method kind of falls apart. Imagine a student body made up of both boys and girls. If a school has 400 boys and 500 girls, those are qualitatively different demographic groups. If you just blindly use that calculator method across all 900 students, random chance might accidentally pick a sample that's like 80% girls. And if you're polling them on something like sports preferences or school uniforms, your survey results are going to be massively skewed, simply because your sample doesn't actually reflect the real makeup of the school.
To fix this, we bring in the layer random sample method. Basically, we divide the population into distinct layers based on their differing characteristics, like splitting up the boys and the girls, or separating first-year students from second-year students. Then, we choose a random sample from within those specific groups so that each layer is represented according to its actual proportional size in the whole population. Honestly, this is the absolute best way to guarantee fair, accurate representation anytime you're dealing with a diverse group.
Which leads us perfectly into our final segment, Section 5, Proportional Math in Action. To actually make this layered method work in the real world, let's unpack the math behind it. Don't worry, it's pretty straightforward. We have our total population of 900 students. Applying our 10% rule, we'd normally want 90, but let's say for this specific survey, we only need a smaller sample size of 45 students total. To figure out exactly how many boys should be in that 45-person sample, we use a simple proportional formula. Take the total number of boys, 400, and divide it by the total population, 900. Then multiply that fraction by our target sample size of 45. The result? Exactly 20 boys. Then we just do the exact same thing for the girls layer. 500 divided by 900 multiplied by 45, which gives us 25 girls. Combine them, 20 boys plus 25 girls, and boom, we have a perfectly balanced, proportionally accurate sample of 45 students. No statistical bias, just perfect mathematical representation.
As we wrap up, I want to leave you with this somewhat provocative thought. If a sample doesn't accurately represent its diverse population, what actually happens to the validity of the data? The scary truth is, if you skip that proportional math in a diverse group, your beautifully collected data might just be telling you a giant statistical lie. These mathematical tools are incredibly powerful, but ultimately they're only as unbiased as the person designing the sample. Definitely keep that in mind the next time you see a sweeping poll on the evening news. Thanks so much for joining me for this explainer. I really hope it helps you decode the statistics in your world just a little bit better.